If you tried to count the atoms in a single grain of salt, you'd be counting for 1,000,000 years without stopping. So how do chemists measure what they can't even see? They need a way to work with these tiny building blocks, even though they are far too small to count one by one. We'll start by seeing what atoms and molecules really are, the invisible building blocks of everything. Then we'll understand why their tiny size is a huge problem for doing chemistry. We'll visualize just how enormous the scale gap is, and finally, we'll preview the clever trick chemists use to bridge that gap every single day. Everything is made of atoms, the smallest possible piece of a chemical element, like a single iron atom. When atoms link together, they form molecules, like a water molecule made of 2 hydrogen atoms and 1 oxygen atom. These particles are so light we measure them in atomic mass units, or AMU. 1 AMU is roughly the mass of a single proton or neutron. It's the basic unit of weight in the atomic world. Imagine baking a cake but your recipe just says add some flour and some sugar. It would never work. Chemistry is the same. To make a medicine or a plastic, you need to mix exact numbers of atoms and molecules. But since we can't count them out individually, we're stuck. We need a bridge that lets us measure a pile of stuff in grams and know exactly how many atoms are inside. To feel the scale, picture a single grain of sand. If we blew it up to the size of a sports stadium, an atom inside that grain would still be smaller than a speck of dust. That's the gap we're dealing with. 1 atomic mass unit is an unimaginably tiny fraction of a gram. You need about 600 billion trillion atoms just to make 1 gram of anything. The numbers are so huge they're hard to say. The solution is a counting by weighing trick, like knowing a dozen eggs weighs about 600 grams, so 1,200 grams means 2 dozen. Chemists use a special number called the mole. If you take the atomic mass from the periodic table, say, carbon is 12 AMU, and measure out exactly 12 grams of carbon, you'll have exactly 1 mole of atoms. It's the bridge that turns the invisible atomic world into something you can hold in your hand. If you had a mole of sheets of paper, you could stack them past Pluto. Chemistry has a counting unit so vast it makes a billion look tiny. Today we're going to unpack this gigantic number. We'll see exactly what a mole is, why it was invented, how it lets us count atoms by weighing them, and where you'll spot it hiding in plain sight on the periodic table. It's a simple idea that turns the invisible world of atoms into something you can hold in your hand. A mole is simply a word for a very specific number of things, just like a pair always means 2 shoes or a dozen always means 12 eggs. 1 mole is 602 sextillion items. That's a 6 followed by 23 zeros. This special number is called Avogadro's number, named after the Italian scientist Amedeo Avogadro, who helped figure out that equal volumes of gases contain equal numbers of particles. So whether you have a mole of atoms, a mole of molecules, or even a mole of marbles, you have exactly this many of them. Atoms are so tiny that you could never count them out one by one in a lab. But you can easily put a pile of something on a scale and weigh it. The mole was chosen to be the bridge between the microscopic world of atoms and the macroscopic world of grams. Here's the magic: if you look up the mass of a single carbon atom in atomic mass units, and then you take exactly 1 mole of carbon atoms, that pile will weigh the same number, but now in grams. This connection is why the mole exists. It turns the invisible mass of 1 atom into a weighable amount you can scoop into a beaker. 1 mole of any substance, carbon atoms, water molecules, or even marbles, contains exactly Avogadro's number of those items. To feel how enormous this is, imagine stacking sheets of paper. If you had a mole of sheets, that's 602 sextillion sheets. This stack would be so tall it would stretch past the orbit of Pluto and keep going, far beyond our solar system. That's the scale we're dealing with. Yet, because atoms are so incredibly small, a mole of carbon atoms fits neatly in the palm of your hand as a small lump of graphite. You can see the mole in action right on the periodic table. Look at the number under an element symbol, that's its atomic mass. For oxygen, it's about 16 atomic mass units. Because of the way the mole is defined, that same number also tells you the mass of 1 mole of that element in grams. So 1 mole of oxygen atoms weighs about 16 grams. This simple relationship means that every time you look at the periodic table, you're seeing a direct conversion factor between the invisible atomic world and the grams on your balance. The whole idea is that the mole is just a chemist's dozen, a counting unit that makes the invisible visible by connecting atomic mass units to grams. If you put a single carbon atom on a scale, it reads 12 atomic mass units. But if you scoop up exactly 1 mole of carbon atoms, the scale reads 12 grams. The number is the same, but the unit has changed. How is that possible? We're going to uncover the secret that connects the tiny world of atoms to the scale in your lab. First we'll define molar mass, then see exactly how the numbers match up, practice finding it for different elements, and finally dodge the most common mistake people make. Molar mass is simply the mass of 1 mole of a substance, and we measure it in grams per mole. Here's the magic: the atomic mass number you see on the periodic table, that number in atomic mass units, is numerically identical to the molar mass in grams per mole. For carbon, 12 AMU per atom means 12 grams per mole of atoms. It's the same number doing double duty. Scientists chose carbon-12 as the anchor for the whole system. 1 atom of carbon-12 has a mass of exactly 12 atomic mass units. Now, Avogadro's number, 6.022 times 10 to the 23, is the special count that bridges the atomic and macroscopic worlds. If you gather exactly that many carbon-12 atoms, their total mass is exactly 12 grams. The number 12 stays the same, only the unit changes from AMU to grams. This scaling factor works for every element. Finding molar mass is as easy as looking at the periodic table. Find the atomic mass number under the element symbol. For oxygen, it's 16.00, so 1 mole of oxygen atoms has a mass of 16.00 grams. For iron, it's 55.85 grams per mole. For gold, it's 196.97 grams per mole. The number you see is the mass of 1 atom in AMU, and also the mass of 1 mole in grams. No calculation needed. The biggest trap is mixing up the mass of a single atom with the mass of a mole. An oxygen atom is 16 AMU, that's unimaginably tiny. But a mole of oxygen atoms is 16 grams, enough to hold in your hand. The number 16 is the same, but the unit tells you which world you're in, AMU for the atomic scale, grams per mole for the lab scale. Remember, the number stays the same, only the unit changes from AMU to grams per mole. A single water molecule is so light it's practically nothing, but add up a mole of them and you can hold it in a tablespoon. How do we bridge that gap? We'll see what molar mass means for a compound, learn the simple summing method, practice with carbon dioxide and table salt, and catch the most common slip-ups. The molar mass of a compound is just the mass of 1 mole of its molecules or formula units. Since a mole always counts the same number of particles, we can find it by adding up the molar masses of every atom in the formula. Think of it like a recipe. If 1 cookie needs 2 chocolate chips and 1 walnut, the mass of a dozen cookies is 12 times the mass of 2 chips plus 1 walnut. Here, the periodic table gives us the mass of 1 mole of each type of atom, and we just add them up according to the formula. Let's walk through water, HO. Step 1. The formula tells us we have 2 hydrogen atoms and 1 oxygen atom. Step 2. From the periodic table, hydrogen's molar mass is 1.01 grams per mole, and oxygen's is 16.0. Step 3. Multiply each by its count and add them up. 2 times 1.01 for hydrogen gives 2.02, plus 16.0 for oxygen gives 18.02 grams per mole. That's the molar mass of water. Now let's try carbon dioxide, CO. One carbon atom has a molar mass of 12.01, and each oxygen is 16.0. So we do 12.01 plus 2 times 16.0, which equals 44.01 grams per mole. For table salt, NaCl, it's even simpler. Sodium is 22.9, chlorine is 35.45, so the sum is 58.4 grams per mole. Notice that whether it's a covalent molecule like CO or an ionic compound like NaCl, the method is exactly the same. Just add up the atomic masses from the formula. The biggest mistake is ignoring the subscripts. If you treat HO as just one hydrogen plus one oxygen, you'd get 1.01 plus 16, which is 17.01, wrong, because you forgot there are two hydrogens. Always multiply each atomic mass by its subscript first. Another slip-up is using the mass number instead of the atomic mass. The mass number is a whole number like 16 for oxygen, but the actual atomic mass on the periodic table is 16.0, which accounts for tiny mass defects and isotopes. Stick to the periodic table values, and double-check those subscripts, and you'll get it right every time. If you had a single grain of sand for every atom in a teaspoon of water, you'd bury the entire planet. So how do chemists count the invisible without losing their minds? They don't count one by one, they weigh a crowd and use a bridge. We'll build a simple roadmap with 3 stops, grams, moles, and particles, and just 2 bridges connecting them. Then we'll walk a real problem together. How many atoms hide in a 24.3 gram lump of magnesium? Finally, we'll flag the traps that trip people up, so you can step right over them. Picture a hub with 3 spokes. In the middle sits the mole, chemistry's counting unit, a packet of 6.022 times 10 to the 23 things. One spoke goes to grams, the mass you can put on a balance. The bridge is molar mass, the grams in 1 mole of that substance, which you read straight off the periodic table. Another spoke goes to particles, actual atoms or molecules. That bridge is Avogadro's number, the fixed count of particles in 1 mole. There is no direct road from grams to particles, every journey must pass through the mole hub. The roadmap is a triangle with moles at the center. To go from grams to moles, you divide by the molar mass, because 1 mole weighs that many grams, so a smaller mass is a fraction of a mole. Once you're at moles, to reach particles you multiply by Avogadro's number. Each mole packs 6.022 times 10 to the 23 particles. If you need to go backwards, from particles to moles, you divide by Avogadro's number. And from moles back to grams, you multiply by the molar mass. The rule is simple, every conversion passes through moles, and the operation flips depending on which way you're walking. Let's solve. How many atoms are in a 24.3 gram sample of magnesium? First, find magnesium on the periodic table. Its atomic mass is 24.3 mu, so its molar mass is 24.3 grams per mole. That's our first bridge. Step 1. Convert grams to moles. Take the mass, 24.3 grams, and divide by the molar mass, 24.3 grams per mole. The grams cancel, and you get exactly 1 mole. Step 2. Convert moles to particles. Multiply 1 mole by Avogadro's number, 6.022 times 10 to the 23 particles per mole. The moles cancel, leaving 6.022 times 10 to the 23 atoms of magnesium. The numbers were chosen to be clean, the mass equals the molar mass, so it's exactly 1 mole, but the method works for any mass. The most common slip is multiplying when you should divide, or the other way around. A quick check: if you're going from grams to moles, the number of moles should be smaller than the number of grams, because 1 mole weighs many grams. If your answer is bigger, you flip the operation. Another trap is trying to jump straight from grams to particles without stopping at moles. There is no direct bridge, you must always pass through the mole hub. Also, double-check you've picked the right molar mass from the periodic table. It's the number with the unit grams per mole, not the atomic number. Finally, always write the units and watch them cancel. If they don't cancel to give you the unit you want, you set up the conversion backwards. So the whole idea is grams to moles to particles, with 2 fixed bridges, molar mass and Avogadro's number, and the mole always at the center. A pharmacist doesn't count individual molecules to make your medicine, they use a bridge between the invisible atomic world and the scale in their hand. That bridge is the mole. It turns a recipe written in atoms into something you can actually weigh out. We're going to see how the mole turns a chemical equation into a practical recipe. First, we'll decode what a balanced equation is really telling us. Then we'll use mole ratios to predict exactly how many grams we need. We'll work through making water from hydrogen and oxygen, and finally see how a pharmacist and a nurse use these ideas every day. A balanced equation like 2H2 plus O2 gives 2H2O isn't just about molecules. The coefficients, those big numbers in front, are mole ratios. They tell us that 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water. It's a recipe that scales up from the atomic world to the lab bench. We already know molar mass connects moles to grams. Hydrogen gas has a molar mass of about 2.02 grams per mole, and oxygen gas is 32.0 grams per mole. Using our 2:1 to 2 mole ratio, we can translate the recipe into mass. 4.0 for grams of hydrogen plus 32 grams of oxygen will make 36.0 for grams of water. The mole is the translator. Let's say we want to make exactly 36 grams of water. First, we find how many moles that is. The molar mass of water is 18.02 grams per mole, so 36 grams is 2 moles. The balanced equation shows a 2:2 ratio between hydrogen and water, so we need 2 moles of hydrogen gas. Multiply by its molar mass, 2.02 grams per mole, and we get 4.0 for grams. We can do the same for oxygen, 1 mole, 32 grams. The mole makes it predictable. In a pharmacy, a prescription might call for 0.01 moles of an active ingredient. The pharmacist uses its molar mass to weigh out the exact grams. Too little and the medicine won't work, too much and it's dangerous. For solutions, we use molarity, which is moles of solute per liter of solution. A nurse hanging a saline for drip checks that it's 0.154 moles of sodium chloride per liter, matching the concentration your body needs. The mole is the silent guardian making sure every dose is safe and effective. A single gram of the lightest gas in existence contains more molecules than there are stars in the entire observable universe, and you can count them all with one simple unit. That unit is the mole, and it turns the impossibly small world of atoms into something you can hold in your hand. It's the bridge between the invisible and the everyday. We've built up the mole piece by piece. Now we'll step back and see the whole picture, what the mole truly is, why chemistry can't work without it, how it links the atomic mass unit to grams, a complete worked example from start to finish, and the chaos that happens if we try to do reactions without it. This is the story of how we make the invisible measurable. The mole is a counting bridge. On one side is the atomic world, where masses are measured in tiny atomic mass units. On the other side is our lab world, where we measure in grams. The mole is simply a specific number, Avogadro's number, about 6.02 times 10 to the 23rd, that connects them. 1 mole of any substance contains that many particles, and its mass in grams equals its atomic mass in mu. It's like a currency exchange that lets us trade atomic weights for weighable amounts. Without the mole, chemistry is blind guessing. You'd have no way to know how much of one substance reacts with another. With the mole, you can predict exactly how many grams of reactant produce how many grams of product. It turns recipes into precise formulas. If a reaction says 2 molecules of hydrogen react with 1 of oxygen, the mole lets you scale that up to grams you can actually measure, making every reaction repeatable and reliable. Here's the chain. Look at the periodic table. Every element has an atomic mass in mu. That same number, in grams, is the mass of 1 mole of that element, its molar mass. For example, carbon is 12.01 mu per atom, so 1 mole of carbon weighs 12.01 grams. And because 1 mole always contains Avogadro's number of particles, you can convert freely between mass in grams, number of moles, and number of atoms or molecules. It's a three-way interchange. Let's do water from start to finish. Water is HO, 2 hydrogens at 1.01 each, plus 1 oxygen at 16.0. That gives a molar mass of 18.02 grams per mole. If you have 36.0 for grams of water, you divide by the molar mass to get 2.0 moles. Then multiply by Avogadro's number, 6.02 times 10 to the 23rd, and you get about 1.20 times 10 to the 24th molecules. Every step is a simple multiplication or division. Imagine trying to run a reaction by counting individual atoms. You'd need to pick out exactly 6.02 times 10 to the 23rd of them, impossible. Or measuring in mu, a single atomic mass unit is about 1.6 times 10 to the negative 24th grams, far below any lab scale. Without the mole, you're stuck. With it, you get clean, predictable stoichiometry, you weigh out grams, the mole handles the counting, and the reaction works every time. The whole idea is, the mole is a practical tool that makes the invisible world of atoms measurable, predictable, and useful.